Hi everyone, this is Mrs. Musoff, and this is going to be our last 4.8 video, the last one of this section, and it's talking about a little bit of a different model. Instead of just uninhibited growth, which was the last exponential model we talked about, this is something called logistic growth. So in the last section with 4.8, we talked about a model for uninhibited growth, and it looked like this: A equals A sub 0 times e to the kt. And this model was meant for uninhibited growth. Sorry, that second one's an N. Uninhibited growth. Alright, meaning nothing was going to stop it. It just kept growing and growing and growing. Alright, but we know that in general there are factors typically restricting the growth, like space to grow or food supply. Right? And that's where the logistic growth model comes into play. So the logistic growth model takes those into account, and basically it recognizes that there's an upper limit to the growth. Alright, so this model here represents the population after time t, where the exponential function is in the denominator, alright, and this c value represents the carrying capacity, which a carrying capacity is basically the upper limit on your growth. Alright, so that's the highest that it would ever get, the maximum population, if we're dealing with population, which usually we are. Okay, the other variables in here, like A, it's just a constant, and B is kind of the important one because B is going to tell us whether it's growth or decay, and it's going to be the rate. So the absolute value of B is our rate, either growth or decay, depending on if B is positive or negative. Alright, now, keep in mind, there is a negative in that equation, so if you see a negative and then a number with t, you know that's actually a positive b value because the negative is already there. Right? And same thing vice versa. So if b is positive, we're dealing with growth. If b is negative, we're dealing with decay. Okay. Like I mentioned, c is our carrying capacity because that's what this entire expression approaches as t approaches infinity. And if you are talking about exponential growth, you'll see a graph kind of similar to the little one that I drew on the other day's notes, but slightly different because it doesn't just grow off into infinity. What happens is it will grow to a certain point and then it will start leveling off. Right? And so that is basically what you would see if we're dealing with logistic growth as opposed to uninhibited growth. Right here is our initial value, p of 0. This asymptote that it looks like it's approaching, that's our carrying capacity, y equals c. And this point right here where it looks like where it changes, we say it changes concavity. It changes from going up to then flipping around and going down. We call that a point of inflection, which will become really important in calculus. Right now we don't do too much with it. Alright, if we're dealing with decay, still relatively similar graph, except it starts decreasing to a certain point. Oops, sorry, that was bad. Starts decreasing to a certain point, and then it starts decreasing slower and slower, and it starts approaching y equals 0, which would be the basically the lower limit for decay. Alright, still we have an initial value over here, and still we have that same inflection point. Alright, so let's try an example with it. Let's go ahead and flip it over. This example deals with the fruit fly population. It says fruit flies are placed in a half-pint milk bottle with a banana for food and yeast plants for food and to provide a stimulus to lay eggs. Suppose that the fruit fly population after t days is given by the formula. State the carrying capacity and the growth rate. Alright, well, carrying capacity we know is our c value, our constant, and it's located at the top of our model. So the carrying capacity is going to be 230 people. Or not people. Yikes. Fruit flies, that's what we're dealing with. Alright, 230 fruit flies is our carrying capacity. All right. The growth rate, on the other hand, growth rate is our b value. That's the value that's up there in the exponent. Now, it is negative. However, remember the negative is already part of the model. So the b is actually just that 0.37, and making it positive, it's talking about growth. So our growth rate is 37%. All right, now part B, determine the initial population. Now, initial population, in order to do that, we're going to have to substitute 0 in for t, initial, meaning t is 0. So we're going to find p of 0. All right, before in the other model, we had a really easy way to find the initial. We don't have that in this model. So we're just going to have to actually substitute it in. No biggie. All right, the nice thing that happens is that entire exponent turns into 0, and e to the 0 turns into 1. So what we have is 230 divided by 1 plus 56.5 times 1, which is just 56.5. Alright, so you would end up with 230 divided by 57.5, which you can calculate. You can throw it in your calculator. That's going to give you 4. So our initial population, we started with just 4 fruit flies. All right, part C, what is the population after 5 days? So once again, 5 days, they're giving us a time. Time is 5. So all we're going to do is substitute it into the formula. Find p of 5. Now, the nice thing again about this formula is if you know time, you could just throw it in your calculator. So like part B, we could have just thrown that in the calculator. This one I'm actually going to, because it's not going to come out quite as nicely as the last one. So looking at that formula, we've got 230 divided by, and then we do need parentheses here, 1 plus 56.5 e to the negative 0.37 times our t, which our time here is 5 days. I'm glad I checked because I was going to type in the wrong number. Oops. And then I'm going to move back down, throw the other parentheses around it, and there's our answer. Now, once again, you can't really have part of a fruit fly, so I'm going to round that down to 23. So p of 5 is going to be 23 fruit flies. Don't forget your units, right? Anytime we're dealing with word problems, make sure your answers have units connected to it. All right, last one. Part D, how long does it take for the population to reach 180? So now it's saying how long, which means I want to solve for t. I don't know what it is. And it's giving me my population. P of t is going to equal 180. So this one I'm going to have to solve by hand. So I'm going to plug it in. 180 equals 230 divided by 1 plus 56.5 e to the negative 0.37 t. Now, remember what we've always dealt with when you have variables in the denominator. The first thing you do is multiply both sides by the entire denominator. So 1 plus 56.5 e to the negative 0.37 t. All right, both sides. And what happens, 0.7t, is over here it cancels out. So over here now I have 180 times the quantity, 1 plus 56.5 e to the negative 0.37 t. And on the other side I just have 230. Now this is kind of similar to some problems we dealt with before. Some of you like to distribute the 180, and that's fine. I prefer to just get rid of it. So divide by the 180 on both sides. Alright, and I get 1 plus 56.5 e to negative 0.37 t. And if I simplify this, I'm just going to leave it as a fraction for now, 23/18. Alright, now all that's left are some basics. Get my base alone, right? This is a base e, get it alone. So to do that, I'm going to subtract 1 e to the negative 0.37 t. 23/18 minus 1, that's like 23/18 minus 18/18, which is 5/18. And then I'll divide by 56.5. And now I'm going to start kind of using decimals because it's going to get a little messier. So 5/18 divided by 56.5. Alright, so we'll go 0.00492, but I'm still going to use that when it comes to actually calculating it. I'm going to natural log both sides. So we have negative 0.37t equals, and back over here I'll take the natural log of my answer. So negative 5.315. And then we'll divide. So we end up with divide by negative 0.37, 14.365. So it will take 14.365 days, remember that was our units, in order for the population to reach 180. Alright, so it's just another type of model. So now we've seen two models. We've seen uninhibited growth and we've seen logistic growth. Alright, so not hopefully, the problem will tell you exactly what type you're dealing with, and hopefully that will give you a sense of which formula to use and how to approach the problem. Alright, that's it for now. Thanks for watching. Write down any questions you have, and I'll see you later.